So the next session, we have Dr. Zheng Lin, Assistant Professor from Department of Semiconductor Engineering, Lunghua University of Science and Technology, Taiwan. And his talk is on advances in device reliability and packaging technologies for high-power gallium nitride high electron mobility transistors. Now I request Dr. Lenin Prakash to introduce Dr. Ru.
Dr. Zheng Lin received his PhD degree in Material Science and Engineering from National Chiao Tung University, Taiwan in 2018. From 2011 to 18, he focused on process and device development of 7 nanometer gate all-around transistors and received the Nano Device Technology Award in Taiwan in year 2014. From 2019 to 24, he worked at Electronics and Optoelectronic Research Laboratories of the Industrial Technology Research Institute, ITRA, in Taiwan, focusing on CMOS compatible GaN on silicon platform and GaN Fetch MOSFETs for power switching application, as well as investigating all reliability issues in GaN power devices. He is currently an assistant professor in the Department of Semiconductor Engineering at Lunghua University and serves as a consultant for Taiwanese Semiconductor Smart Sensing Company. I invite Dr. Zheng Lin to deliver his expert address. Please, sir.
Okay, thanks, Dr. John and Dr. Zheng Lin. And good afternoon, everyone. It's my great honor to be invited to the workshop on the semiconductor packaging and testing, jointly organized by Sastra University of and the Lunghua University of Science and Technology. Today, my presentation topic is advance in device and reliability and packaging technology for high power GaN HEMT. I will be share with you the recent development of the GaN HEMT power device, their critical role in power conversion, switching, and the discussion their advancement from the perspective of the device technology reliability and the packaging. Okay, so to begin, I would like to introduce myself. I'm Zheng Lin, and I'm current assistant professor in Lunghua. Yes, so my current research primarily focus on the advanced wideband gap semiconductor process and application, particularly in the development of the GaN on silicon carbide, and the QST substrate for high power and high frequency device. At the same time, I'm working extending semiconductor technology to the biosensing application, exploring their potential in medical and health diagnostic. In addition, I'm also development of the nano electrode device, expected design and application of 2D thin transistor. Okay, in this talk, since module packaging is not my main research, so I have still prepared some related material to share with you today. So if you any question, please feel free to email to me, and I will provide you a detailed reply. Okay, this is outline. Today I will talk about the GaN HEMT introduction and about the background review. And the GaN-based HEMT power device structure, I will give you some experience. And in the power device, we will focus on the stability, reliability, and the robustness in the GaN HEMT power device. So after the next I will talk about the advanced packaging technology of the GaN HEMT module, and I will give the conclusion. Okay, so to begin with, so we can clearly see from this chart, global electricity consumption is a project to grow the significant over the coming decades. It is estimated that within the next 20 years, electronic consumption will account for around 6% of total energy use, reaching a astonishing 49,275 terawatt hours by 2050. This growth spans across industry, transport, building, and other sections. In the face of the such rapidly increased demand, the development of the electric power conversion device must primarily reduce loss and improve the conversion efficiency. This is not only the crucial for enhanced energy utilization, but also play a direct role in achieving a global carbon reduction target and advance sustainable development. Okay, we show this figure is about the wide bandgap device from the different material. So we can see the in the low inflation and high inflation in here. So silicon dominate in the market, support the development of the IGBT and the super junction MOSFET. However, silicon has already reached its physical limits in terms of the efficiency and the breakdown voltage. So gallium nitride and the silicon carbide have already achieved a significant progress in the market. Gallium nitride is mainly used in the 100 to 900 volt range, moving toward 1.2 kilovolt and 1.7 kilovolt. Silicon carbide cover higher voltage from 600 volt up to the 3 kilovolt, and is progressing toward the 6.5 kilovolt, making it particularly suitable for high voltage and high efficiency application. Looking forward ahead, ultra wide bandgap material are emerging. Gallium arsenide, diamond, and aluminum nitride per aluminum gallium nitride have offer over wider bandgap and excellent thermal properties. Also still under development, they show great potential for the next generation high voltage and high efficiency power electrodes. Okay, let me see this. So I will introduce tell you the characteristic of the wide bandgap device called the silicon carbide, gallium nitride, and the system. This figure is about the relation of the gate charge and the unresistant. Okay, so these parameters are critical performance indicator from this result. This is clear. Let GaN HEMT demonstrate significant advantage in low and medium voltage application. They offer higher switch speed, lower loss, and overall superior performance, making them an excellent choice for the next generation. Okay, you can see here. Okay, so next, let's discuss the performance comparison of the different wide bandgap power device in terms of the breakdown voltage and the specific unresistant. From this chart, we can see that the silicon device are limited by their material property. At higher breakdown voltage, the specific unresistant increases sharply, which corresponds to the silicon limit. In concentrate, silicon carbide device can maintain much lower specific unresistant at high voltage, clearly outperforming silicon and approaching the silicon carbide limit curve. So the gallium nitride device demonstrate particularly outstanding performance in the medium to low voltage range, especially into the 600 volt and the 650 volt classes, where the specific unresistant is experiencing low far below that the silicon and the silicon device at the same voltage level. This enable again to deliver ultra low loss and high efficiency character, making it highly suitable for high frequency switching and high power density power electronic system. So the red arrow label the desired direction in the chart indicate the ideal development goal to further reduce specific unresistant while maintain and or increasing the breakdown voltage, thereby enhance overall device performance is remain one of the key direction in ongoing power semiconductor research and development. Okay, so let us now take a closer look at the different in application dominant and invention among various power semiconductor materials. On the left hand side of the chart, silicon is primarily used in the low power, low frequency applications such as the AC/DC power supply and the small PV microinverter. However, as demand increase toward higher power and higher frequency, the performance limitation of the silicon material become more evident. Silicon carbide stand out in the high power applications such as the wide turbines, railway, traction, and industrial and EV, electric hybrid vehicle, where it can the high voltage will maintain high frequency. So in contrast, gallium nitride demonstrates significant advance in the high frequency and high efficiency application, making it especially well studied for data center, DC to DC conversion, PC power conversion, and the PV microinverter that require the faster switching. So the chart one on the right light the reliability during the AI data center, which could achieve the substantial infinity gains if the GaN device and adapt in the future. Traditional silicon-based data center after ongoing multiple volt conversion stage typically reach an overall efficiency of about 75%. In comparison, gallium nitride-based data center with more efficient AC to DC and the DC to DC conversion stage can achieve an overall finishing of the 84% improvement of the near 10%. This boost in finishing not only reduce energy consumption and the operating cost, but also direct lower carbon emission. Okay, making it highly significant for the development of the future green data center. Okay, so let us compare the global value forecast the gallium nitride and the silicon carbide power semiconductor from 1918 and 2029. From this trade, the application of the gallium nitride and the silicon carbide in power electro field are expected to grow rapidly, with the marketing size project to surpass $5 billion USD by 2029. The different color present various application sector with band growth driver coming from the hybrid and the pure electronics vehicle and the PV inverter, as well as commercial vehicle and the industrial motor driver. In addition, military and aerospace, UPS and data center, HEV charging in faster charger and the power supply will be also key contribution to make the expansion. It is worth nothing like the start in the 2023. The slope of the curve increased signification indication accelerated market demand. This is primarily driven by the rising penetration or the review, the energy and the rapid adoption of the electro transportation, which have the sped up the adoption of the gallium nitride and silicon nitride technology. This suggests that in the coming decade, this two wide bandgap material will not only replace certain silicon-based device, but also become core technology for high efficiency and high power application. Okay, so we in this slide we will focus on the structure and the development of the GaN-based HEMT power device. So first we talk about the normally on silicon HEMT device. This device is built on the silicon substrate on which the L-GaN buffer layer with the sync of the process 1 to 5 micrometer is deposition release and lattice mismatch stretch. On top of this, the GaN channel UID GaN is grown, which serves as a key to achieving high electromobility in here. So to further enhance performance, the thin aluminum nitride spacer layer about 0.7 to 1.2 nanometer thick is insert built-in GaN channel and the upper barrier layer and improving the concentration and the mobility of the 2DEG. 2DEG growth in here. Finally, the 15 to 30 nanometer L-GaN barrier layer with the aluminum constant typically ranging from the 50% to the 40% is the deficit. This barrier induces strong polarization effect there by forming the high density 2DEG channel in here. Okay, so we explain the operation mechanism of the normally on device structure in here. So and the aluminum GaN and the gallium nitride interface due to the piezoelectric property of the material, the combined effect strong polarization file and the band gap offset cause the energy band to bend down downward, forming a quantum well in the GaN channel. This quantum well confines a high concentration of the electron within extremely thin region, thereby generating what is known as 2DEG in the UID GaN layer. The presence of the 2DEG is the key to achieve high electromobility and low on resistance, both of which are essential characteristics for high frequency and high power applications. Okay, so let's now look at the operation principle to control the current. The circuit gate is apply the sufficiently negative gate bias. We can increase the circuit very high with the shift and the conductance band upward. This action effectively deplete the 2DG channel under the gate region, a pitch of the current path and turning the device off. So you can see IDVG showed here when the negative charge from the gate voltage, it will close the current. Okay, this gate control capability is critical for power switching application, allowing the device to combine low on resistance in the conductance with high blocking capability when turned off. Okay, so next, this slide explains the normally of the GaN HEMT structure in the power switching system. Normally of device is more favored due to their high safety and elimination of the static power consumption in the absence of the gate voltage. So normally of device remain in the off state and only turn on the positive gate bias is applied, which is particularly important for high voltage circuit and protecting mechanism. So in population, we can see the structure normally of the GaN HEMT structure have the p-GaN gate and the recessed gate means HEMT, and we can use the foreign ion GaN in here, and the thin and ultra thin barrier HEMT structure in here. We can get the normally of the GaN HEMT structure in here. Okay, so among these structure, the p-GaN or the PL-GaN gate structure is currently the main research focused on the normally of case, as it offers relatively simple structure, good reliability, and compatibility with the existing fabrication technology, making it a key area of the insert in the both industry and academia. Okay, so in this slide we talk about the principle and the characteristic of the p-GaN and L-GaN gate. In this structure, the energy doped in the p-type as the p-type as a gate structure in here. Owing to the higher Fermi level of the p-type layer, the 2TEG benefit the gate is depleted, keep the device in the off state when no gate voltage is applied. When a positive gate voltage is applied, the 2TEG the gate is restored, creating a conduction path and thereby achievement normally of the operation. The energy band diagram on the slide clearly illustrates the modulation effect of the p-GaN layer on the band structure. When IV curve demonstrates the sharp increase in drain current once the gate voltage exceeds the threshold voltage. With its high reliability, excellent normally of the correct and compatibility with the mature fabrication process. This structure has become one of the mainstream development direct for GaN power device in the industry. Okay, so next I'd like to share with you the three key aspects of the GaN HEMT power device about the stability, reliability, and robustness. Let's first look at the future. The dash box replaces the safe operation area we call the SOA, which defines the safe range of the operation under the relative voltage and the current. Each of the three aspects is closely related to this SOA. So first, we talk about stability. Stability tests are usually conducted with the SOA. We monitor the parameters such as the dynamic on resistance, threshold voltage, and the output capacitance during switching operation. These variations are mainly caused by carrier trapping and de-trapping, and they are temporary. Once the stress is removed, the device recovers and no parameter damage occurs. Okay, second, we explain the reliability. Reliability tests are typically carried out near the boundary of the SOA. In this case, most server conditions are applied, such as high temperature operating life, we call HTOL, and high temperature reverse bias, we call HTRB, and the long-term switching stretch, we call the TDDB. The goal is to examine whether the device undergoes irreversible degradation or approach failure after extending operation under the heavy load. Okay, third, we talk about the robustness. Robustness test go behind the SOA, pushing the device to its ultimate failure limit. Common example include ESD, available breakdown, and show circuit events. These tests reveal how much stress the device can tolerate and where is the several limits under the extreme condition. So together, these three aspects from the complete framework is evaluation, quality, and the development of the GaN HEMT power device. Okay, so let's use the illustration to understand the common failure location and mechanism in the GaN HEMT device. So first, in the GaN region, in this area, electro and hole trapping, electrothermal failure, and impact ionization may occur. Their effect weaken gate control, result in the increased gate leakage current and the schedule voltage shift. So second, in the hero junction and the interface, L GaN and the dielectric per GaN interface trap affect the concentration and the distribution of the 2D in the channel, leading to increase the dynamic on resistance and the deterioration of the output characteristic. So third, in the GaN buffer layer, possibly failure mechanism including buffer trap, impact ionization, and percolation leakage. This issue rise leakage current cause the localized overheating and reduce the long-term reliability. For in the transition layer and the silicon substrate, in the transition layer and the silicon substrate leakage and the interface trap may development impedance device isolation capability and breakdown performance, especially critical in high voltage applications. Okay, so next I would like to introduce some of the latest development in the advanced GaN HEMT module packaging technology. Okay, in this slide, I will summarize several common use substrate available on the market, including the PCB, IMS, and the DBC. Is the ceramic metallized substrate include the three structure. In particle GaN HEMT module packaging application, the most widely used substrate still the PCB, IMS, and the DBC. So I will now go through the characteristics of these three substrate in the detail. First, let's look at the multi-layer, the PCB. They are flexible in design and can reduce the perimeter effect. But the layer thermal conductivity is very low, only about 0.3 watt per millicalorie. So the heat dissipation is limited. Even with the thermal rise or copper inlays, the performance is still much worse than the ceramic and metal substrates. And the next, we talk about the DBC, which has the copper ceramic copper sandwich structure. It provides both excellent thermal conductivity and isolation, and very reliable for the hitting high current and high voltage. IMS, okay, when we talk about IMS, IMS is the middle ground solution between the PCB and the DBC. It has better thermal performance than PCB with conductivity of about 3 to 7 watt per millicalorie, while still being cost effective and easy to manufacture using the IMS and the DVC can reduce the thermal resistivity by 17% to 18% compared with the PCB. So finally, ceramic metal structure MB offer the best thermal and magnetic strength, ideal and high power application. DPC on the other hand, support very fine circle patterns, making it suitable for lower current modulate that need higher resistance density. Okay, as present, GaN HEMT module packaging structure can generation be divided to the seven major categories. So first, we introduce the packaging structure based on the PCB technology. Current module packaging technology PCB surface mount technology SMT was one of the earliest approach to be adopted. Companions such as EPC and the GaN system use this mouse, where GaN device are mounted direct onto the PCB using the solder bonds. The advances are the simple processing and the low cost, but a careful PCB layout design is a requirement. Otherwise, parasitic inductance can degrade the performance. In particular, four common PCB loop layout are used: lateral, vertical design, hybrid, and the mirror design. First, the lateral layout is the device the capacitor on the same side, easy for thermal vice, but higher loop inductance. Vertical layout is the device and the capacitance on the opposite side, very low in inductance, but limit cooling operation. Hybrid layout is combined with using the inner PCB layer for magnetic cancellation, which along bottom side cooling. Minimal layout is the semiconductor placement on the both sides, lowest introduced, and good thermal performance, mainly for soft switching applications. Okay, so next, let's talk about the wire binding packaging. It has been the most common connection method in power module because it's very simple, mature, and reliable. However, the high frequency GaN HEMT is a drawback, stand out high parasitic inductance, extra unresistant, and a larger footprint. Typically, bond wire and terminal can add more than 15 to 13 nanofarad, leading to higher loss and switching loss. A conventional wire bonding structure uses the DBC structure on the hand stick, but the loop endurance can still reach about the 5 nanofarad. Recent improvement integrated busbar with the capacitor and the drivers, cutting inductance around 3 to 4 nanofarad through bond wire eliminations. Okay, let's introduce the flip chip packaging. Unlike wire bonding, it uses short solder bond, which greatly shorten the loop length, lower parasitic inductance, and enable high density integration. A study showed that flip chip packaging have a 6 times lower inductance and 15 times lower resistance than wire-bound ones, highlighting its clear advance. However, its thermal performance is limited, making it more suitable for low power application. Okay, so let's talk about the PCB embedded packaging. In this design, the GaN device is embedded in the PCB and connected through the micro vials, which free up surface space for driver and capacitors, and offer better voltage isolation. This approach has gained wide attention due to its potential for low parasitic inductance and high integration. Example include three-phase inverter, vertical multi-layer PCB design with the sub 1 nanohenry inductance and the 4 birch modules, achieving as low as the 0.3 nanohenry with the excellent thermal performance. However, excellent remain manufacturer is the complex FR4 has poor thermal conductivity and the CTE mismatch limits reliability. Okay, so we continue to talk about the enhancing thermal performance. A common solution is the integration device on the ceramic substrate such as DBC, AMB, and DPC. Among them, DBC packaging is the most attractive for the high power GaN HEMT thanks to its excellent thermal performance, low cost, and metal progress. By placing the GaN die driver and the capacitor directly on the DBC, the loop inductance can drop from the 20 nanohenry to about 5 nanohenry, while enabling high integration. Advanced designs such as BEODBC, a stack loop, or aluminum nitride DPC double side cooling can push the inductance below 1 nanohenry and achieve a very high efficiency. Overall, ceramic substrate provide outstanding thermal benefits, but are less flexible in the circuit design than PCB. So balance between thermal and electrical performance is always a need. Okay, so next we talk about IMS structure in the GaN packaging. IMS can be seen as the comprising between PCB and the DBC, offer good thermal performance, design flexibility, and cost effectiveness. A good example is the GaN system. GaN systems use the 650 volt per 120 ampere healthy birch module, which integrate drivers capacitors on the top and use distribute decouple and 6-layer PCB and flux cancellation to the minimize inductance. In terms of the thermal performance, IMS reduce the thermal resistance by about 75% compared to PCB with the vice and 50% compared to the Cooper inlay PCB, thanks to its thermal conductivity of the 3 to 7 watt per millicurie, much higher than FR4. It's also lower assembling cost by removing extra heat and sink and pads. Also not as the thermally conductive as the DMC. IMS is higher dielectric strength and can handle high voltage with within dielectric, making it a well-balanced solution for cost, performance, and the design flexibility. Okay, so finally, let's talk about the hybrid PCB on DBC structure. Multi-layer PCB achieves low inductance but poor heat dissipation, while DBC offer excellent thermal conductivity but higher inductance. The hybrid approach combines the best both. In this design, the top PCB interposer connect device terminal, while the bottom aluminum nitride DBC provide heat dissipation. This reduce parameter induce inductance to about 1.2 nanofarad and 3.5 nanofarad. Following improvements such as replacing pins with the silver rod and the integration gate driver push inductance below 1 nanofarad and the resistance below 1.5 milliohm, while thermal resistance dropped to the 0.26 degree per watt. Using advanced material like the sinter silver with the LNDBC and the silicon nitride AMB further enhance thermal design, achieving the thermal resistance as below as the 0.15 degree per watt. This makes the hybrid PCB on DBC structure highly promising for high power GaN modules. Okay, so in today's talk, I would like to summarize 4 main conclusions. So first, enhanced mode, we call normally of the GaN device, have become the industry standard. In particular, the P-GaN HEMT structure offer the operation safety and the high performance, making the especially suitable for high voltage power conversion application. Two, also the GaN has the high potential. Its reliability still require continuous improvement, which can be achieved through tests such as the HTRB and the HTGB and the TDDB. Advanced packaging technology are critical, converting substrates such as the PCB, IMS, and the DBC, as well as the innovative approach like the flip chip PCB embedded and the hybrid PCB on the DBC. This solution to the balance parameter inductance reduction, thermal mechanism, and the cost control. And GaN will drive higher finishing and minimization with the application in data center, electric vehicle, renewable energy, and the power conversion system, and is expected to become core technology for high performance power electronics in the next decade. Okay, this is my my talk. Thanks.
Thank you, Professor Franklin. Thanks for the great session. So
Okay.
that's a question. There is a question for you. So when do you think this GaN HEMT will be available for a commercial device? So is there any specific challenging in commercializing this GaN HEMT?
Yes. You mean the GaN HEMT device in the future? We have the challenging in the structure.
Yeah, I mean, it's like so. When do you think it will be available in a commercial scale? So, is there any specific challenges in terms of packaging for this device to available in a commercial scale in the future?
Yes. in the future, I think I will check and I prepare and I reply this question.
Okay, okay. So thank you, Professor. So thanks for your great session. Thanks for your time.
Excuse me. May I have some question? Okay.
Yes, please. Yes, please. Yeah.
Okay. Thank you. First, thank you for your insight for the presentation. So I have two questions for you. First one question is how to increase the breakdown voltage in the lateral GaN HEMT structure?
Okay, that's a good question. I didn't indicate the part of my yearly content list, so I explain it here. So we can enhance the breakdown of multiple. I show this. Okay. Common technology that expand the metal field plane from the gate, source, or jet. These file planes, such as gate file planes, source connect file plane, or the multiple file plane, help to redistribute the electron file more evenly and support the peak file concentration. Another approach is the increase the gate to drain the spacing, which reflecting the electro file distribution and the improvement breakdown voltage. Of course, it comes at the cost of the higher on resistance in here. From the another is from the is the structure. Several structures can be adapted. For example, carbon doped the GaN buffer layer, super lattice buffer layer, high quality expansion material, high quality gate dielectric, and the surface preservation layer. So I think this methods can increase the breakdown voltage.
Okay, thank you. My other one question is which GaN HEMT module packaging structure is considered the best at the current stage?
Okay, I think there isn't a single definitive answer. Packaging structure for GaN HEMT is really depend on how you balance the power level, voltage, thermal performance, parameters, inductance, integration, and the cost. So for high power and high voltage application, DBC and AMB structure are the mainstream the choice. If you need both excellent thermal management and ultra low resistance and hybrid PCB on DBC structure shows the most promise. For cost sensitive medium to low power design, IMS is the particle solution. So finally, if you go a high frequency operation of miniaturization, flip chip or PCB embedded packaging is the most suitable approach. So that's my request. Thank you.
Okay, thank you.
Okay.
Yes,
Yeah.
yes. Thank you. Thank you.
Thank you.
So thank you, Professor Franklin. Thank you. Thanks for joining and thanks for your time. So really enjoyed your session with your insights. And thanks, Professor Paul Chang from Lungwa, for your question. Thank you.